In this week's exercises, we're going to use this dataset ICU-origin cvs.csv that you can find in the dataset folder. This dataset includes patients that were admitted to the ICU. We're going to focus in this variable vital status at the hospital discharge with outcomes 0 that survived the ICU or the hospital stay, and 1 that did not survive or died. Okay, and we have several other variables that we're going to also to use throughout the exercises. So the first exercise is going to compare a model where age is fitted with as a linear effect in the logit scale, so a usual linear effect in the logistic regression to model the probability of not surviving the ICU, and compare it with age fitted as a categorical variable. Okay, so let's open this data, and the first thing that that we need to do is to import the data. You can do this through the menus, but I'm just going to run here the import command. So the data was imported. You can see here the data imported. The first table in the exercise tells you the coding of each one of these variables. So the first thing we want to do then is to fit this regression model for discharge status with age as continuous, systolic, hand type, and log as other covariates. Okay, so we're not going to really focus much on the interpretation of the results, but more on the tools to build these models. So let's run a logistic regression for STA. So logistic regression, STA, and the variables, we can write them here, age, systolic, can, log, type, and log. And because these three last variables covariates are categorical, we should add this I dot to create the dummy, the indicator variables for the categories. Okay, so I'll run the logistic regression. I got the results here, so I have the different odds ratios associated with the variables in the model. There's a note here saying that 5 observations were dropped, and the reason for this is that if you do a table for the variable log, so looking at frequency by discharge status, so STA, you'll see the category 1. In category 1, everyone died. So the probability of dying in this category is 100%. And the logistic regression has problems to model 100% and 0%. So if you think about the logit curve, that S curve that we are fitting to our data, that curve never touches 1 or 100% and never touches 0%. Okay, so the model cannot really reach to 100%, and that's why it gets into problems. And Stata decides to drop those cases and just fit for location 0 and 2. Okay, so this one is empty, there's no one, and this odds ratio here means that the location 2 is 11 times higher odds of dying when compared to location 0, which is the reference category. Okay, so going back to the logistic model, we fitted the logistic model, and now we want to estimate the AIC and BIC for this model. So if I come to the post estimation command, you can find here the different things. In diagnostics, we'll get information criteria, and in the new box, information criteria. Okay, so that's what you want. And I'm going to fix this line of code because we're going to use it throughout different models. So stat IC gives us the AIC and BIC of the last model that we run in Stata. Okay, so we run logistic regression, we write this, and I get the AIC and BIC for this model. So I cannot interpret these AIC and BIC by themselves. I can only interpret the AIC and BIC comparing to other models. Okay, So the 1C asks us to refit the model, but now using age as a categorical variable. And I don't specify which categories, so it's really up to you. I'll first have a look at the histogram for age, just to have an idea about the distribution of the variable. And it's really up to you where to draw the cuts for the categorical variable. You could use quartiles or quintiles, or just decide on the categories. Let's say below 40, below 60, below 80, and below 100, something like this. So let's create that variable, data, create new variable extended. It's the command here. The variable is going to be called ageCat, and I'm going to use this cut function applied to the variable age, and the cuts are going to be at 0, 40, 60, 80, and 100. Okay. So there's a new variable called ageCat. You can quickly have a look at it. So tab ageCat will give me the table of frequency. And it's not evenly distributed, but that was not the objective also. So these were the categories that I decided to use. And now I want to refit the model with this variable instead of the age as continuous, okay? So I'm coming here to my history, and just to recover the logistic model. And instead of running the age, I'm going to run ageCat. And because this is a categorical variable, I'm going to add y dot. Okay. So again, the 5 cases were deleted because there was everyone died in category 1 of the variable lock. And you can look now at the effect of different categories of age, and you can see that the odds ratio is increasing from the reference category up to the last category. And of course, this doesn't tell you that the effect is absolutely linear, but at least it goes in an increasing direction. So it's monotonic, this effect. So this is a way of having a simple approach or simple look to the effect of age as continuous, because if there was the effect of age as linear, because if the effect was something like, you know, increasing up to a certain point the probability of dying and then decreasing after a certain age, you'd see this in the categories, unless you have selected the wrong categories. So again, this is sort of a naive approach to look at this. We'll have other tools that we'll explore in the next exercises. But just let's ask the AIC and BIC for this model now, and compare it with the model where age enters as a continuous variable in the linear effect. So stat IC will give us the AIC and BIC for the last model that we run. So the AIC for this model is 145. If you compare it with 140 with this criteria, this model is better. The model with age as a linear effect is better than these categories. And one reason for that is that we have many more parameters in this model. We have 1, 2, 3 parameters for the effect of age, where here we just have 1 parameter. So the AIC is penalizing this model because of the number of parameters. So the model with age as a linear effect wins this criteria. And the same thing happens with the BIC. Okay, this also has the lowest BIC. So we answered E, and now we want to answer F, investigate linear assumption for age. So now there's different tools that we can use. This would be one of them that gives us a rough idea if it's reasonable to have age as a linear effect. But we have other tools. We could explore it graphically, looking at the lowest curve in the scatter plot and comparing with the predictive values from the model with age as linear. We'll see something like that in one of the next exercises. But I'll prefer to use the fractional polynomials because that's what we've been using through in the lecture or been exploring the lecture. So I'm going to use the fractional polynomials to explore the defect of age, the shape of the defect of age. Okay, so I'm going to fit a fractional polynomial, and I get fractional polynomials in the linear models, which is a bit surprising, but here there's no fractional polynomials. So I have to come here to get the fractional polynomial command. Fractional polynomials regression. I'm going to do reset here. So the variable that I want the fractional polynomials to be created on is the variable age, and the command is going to be the logistic of sta age in between the less and more than symbols, because I want the age to be replaced with the fractional polynomials, and then the other variables. So sys.ican itype nalloc. Okay, there's something that we have to add in this new commands, and I don't really understand why. I think it's still a programming issue of Stata with new commands and the way things were working before. In these new commands, you actually you have to force the creation of these indicator variables. So if you run it like this, it won't really work. So you have to add this xi two dots before the command, and this forces the creation of these indicator variables. Okay, so I don't think there's really a logical explanation for adding this, but you really need to add, otherwise you'll get a different address. Okay, so Stata is fitting all the models with fractional polynomials of degree 2, that's the default, and also fractional polynomials of degree 1, so fp2 and fp1. Fits also the linear model, so the logistic regression with age in the model as a linear effect, and the model, the same model, but without age, without the variable age. Okay, so now you have the result here for the fractional polynomial of degree 2, but let's focus first on this table because we want to decide if we really need the fractional polynomials or not, or if the effect of age might be considered to be linear. So we can use several criteria. We can either use this hypothesis testing criteria, or we can use the AIC or BIC criteria. Okay, so I'm going through first through this hypothesis tests, and then we'll see the AIC and BIC. So the reference model here is going to be the FP2, so fractional polynomial with degree 2. Okay, and this is fitting a model with so if you recall from the lecture, power of 0 corresponds to log of the variable, so it's fitting the model with the log of age, and a repetition, it'd be the log of age times the log of age. So it's going to be log of age and log of age squared, basically. Okay, so this is the model that has been fitted. FP1 is fitting the model with age squared. Okay, so as I was saying, this FP2 is going to be the reference model, and what this test here is doing is comparing FP2 with FP1, FP2 with the linear model, and FP2 with the model with age omitted. Okay, and what this result tells me is that the data does not support FP2 over FP1. Okay, so we accept null hypothesis that both models are equivalent in terms of deviance. Okay, so because FP1 is a simpler model, I'll prefer FP1 because, again, the data does not support the higher complexity of FP2. Okay, so the next step would be now to compare FP1 with linear, but I don't have that effect, that test. Okay, the only test that I have is FP2 versus linear, is this P here, which is also non-significant, okay? But I really want now this model versus the linear. So what I'll do is I'm going to rerun the same model, but I'm going to add, of course, just dimension 1. So I just want fractional polynomial of the dimension 1, and I'll add this replace, because the FP command creates auxiliary variables for age, and if I don't put replace, it will give me an error saying that the variables are already created. So okay, and here we go, and now I have the test comparing the FP1 with linear, and the same thing happens. So basically the data is not supporting the more complex model, it accepts the equality of the deviance of the two models. Okay, so the linear model seems, the linear effect for age seems to be sufficient. So we could have done the AIC criteria as well. So if I go back to the model for FP2, I'm just adding the replace for the same reason. So I'm refitting now fractional polynomial of degree 2. So we're back with fractional polynomials of degree 2. This is the output of that model. So if I do stat IC, I'll get the AIC BIC for this model. Okay, so if now I do the FP1, so FP with dimension 1, I'll run. Now this result refers to the FP1 model, and if I ask for the AIC and BIC, I get the AIC and BIC, and again the AIC and BIC criteria tells me the same thing. So the model, the FP1 is actually AIC lower than the FP2. Very similar, but still lower. So I'll prefer this model of FP1 over the FP2. Okay, now I would like to compare this with the linear model. So let's fit the linear model, be something like this. Linear model is logistic model with the linear effect for age, right? I think you understand what I'm saying. So this is the linear effect for age, stat IC, and this is the IC for the linear model. And you can see that this one is slightly, the FP1 is slightly lower, but it's really it's 0.6 difference in the IC, so virtually identical. And the reason for that is, despite of the FP1 being more complex because there's a transformation of age, in terms of parameters, it's the two models are identical. So that's why the FP1 does not get highly penalized, because it has virtually the same number of parameters as the linear effect. Okay, so it's really a matter of choice. I would probably go for the linear model because of the interpretation, right? So this one I can interpret. This is the increase on the chances of dying per age. So increase about 4% per year of in the variable age. The FP1 fits a model with age squared. That's the model that was fitted, the best one, and it's not really interpretable, right? So this is really not an odds ratio, because the odds ratio will be increasing with age. It's not really linear. So I'll probably prefer the age as linear effect, because it's a model that is more interpretable than the previous one. Okay, so this was exercise 1.